Okay, next is 5.5, linear dependence and independence. Okay, definition of linear dependence and independence. Let C1 plus C1 V1 plus C2 V2 plus CK VK equals 0. A linear combination of V1, V2 until VK is 0. So a set of vector V1, V2, VK is linearly dependent if there are scalars C1, C2, Ck, at least one of which is not 0. So if a linear combination, when a linear combination of Vi is set to 0, if at least any Ci scalar at least one is not 0, so we call Vi is linearly dependent. Okay, example. If V1 given by this, V2 as this, and V3 as this one, okay, in R4, then the set of vectors V1, V2, V3 is linearly dependent, since we can set 3V1 plus V2 minus V3 equal 0. Okay, so we can see that C1 is 3, C2 is 1, and C3 is negative 1. So all not 0, so therefore V1, V2, V3 is linearly dependent. Okay, so this one you can find value for 3, 1 and minus 1 here by set the equation CV1 V1 plus C2 V2 plus C3 V3 equal to 0, and solve system of equation. Okay, remember system equation, how we set system of equations to 0 and solve set of system linear equation and find C1, C2 and C3. Okay, take an example. Consider the vector I, J and K in R3. In terms of components, the vector equation K1I plus K2J plus K3K. When it is set to 0, so we have this, when it is set to 0, and solve this equation to find K1, K2, K3, and lastly, we have K1, K2, K3 is 0, all is 0. So therefore, I, J, and K is linearly independent. Okay, since none of the K here is not 0, since all are 0, we call V1, I, J, and K are linearly independent. Okay, next example. Determine linear independence or dependence for these given vectors V1, V2, and V3. Okay, now determine this. Okay, so we set to 0, K1, V1 plus K2, V2 plus K3, V3 set to 0. So we have this one, this equation. And then try to find and get the system of linear equation like this. Solve the system of linear equation to find K1, K2, and K3. Having this one, so finally we have got this one. So since we have the system has, so since we have this these solutions, so the system has non-trivial solution. Since non-trivial solution meaning that we can set the any real numbers, so it means that all K1, K2, K3 may not be 0. Since we can set T as 1, so K1 become negative half. Okay, K2 become negative half and K3 is 1. Okay, so therefore V1, V2 and V3 are linearly dependent set, since we have a non-trivial solution. Okay, 5.6, basis and dimensions. So definition of basis for vector space, subset W of a vector space V is a basis for V if number 1, W spans V, and second, W is linearly independent. Okay, remember spanning set in 5.4 and linearly independent in 5.5. Okay, so if these two conditions are met, then we say W is a vector. W is a W in vector space V is a basis for V. Okay, standard basis for n space. Example, let J, K and S as these vectors. Then S is linearly independent and span R3. So S is the basis for R3. Okay, since S vector ijk, then S is linearly independent and span R3. So S is the basis for R3. And S is called the standard basis for R3. It means that any vector V, component A, B, C in R3 can be written as a linear combination of I, J and K. Okay, right. Example, let V1, V2 and V3 be these vectors. Now show that the set S of V1, V2 and V3 is a basis for R3. Okay, solution. Let B, B1, B2, B3 be any vector in R3. Okay, so if B is written in a linear combination of V1, V2 and V3, so we have B1, B2, B3 and the right side is this one, the form of linear combination of this. Okay, now, so we have this equation of the linear combination and put this in a system of linear equation form and then take the determinant of this. Since the determinant of metric coefficient here is -1 and since it has since the determinant is not 0, so for this is AX equal B. This is a non-homogeneous system. Since a determinant for non-homogeneous system is not 0, and we can have the homogeneous form, which is AX equal to 0, has a trivial solution. Okay, so we can check, refer back notes 20 on the properties of linear equation. Okay, check back, refer to this page. If the AX equal the non-homogeneous system, the determinant is not 0, so we have the other equation, which is homogeneous system, AX equal to 0, that has a trivial solution. Mean that all solutions of C1, C2 and C3 becomes 0. Okay, so since all the solution for C1, C2 and C3 is 0, it means that V1, V2, V3 is linearly independent. Okay, so AX equal to B has a unique solution. When AX equal to B has a unique solution, it means that as V1, V2, V3 is linearly independent. When V1, V2, V3 is linearly independent, we can say that S spans R3. Okay, so since S spans R3, and V1, V2, V3 is a basis for R3. So the two condition for basis are met. Two conditions for basis, which is it is spanning set. S is a spanning set in R3 and S is linearly independent. So we can say that S, which consists of vector V1, V2, V3, form a basis for R3. Okay, example 2, let S be V1, V2 and V3, basis for R3. In example 1 earlier, okay, now find the coordinate vector of V with respect to S. And B, find the vector V in R3 whose coordinate vector with respect to the basis S is given by -1, 3 and 2. Okay, solution. Let V become a combination vector V1, V2 and V3 as this. And put back the component of vectors here and write in the form of system of equation and solve this. So once we solve this, the answer will get C1 is 1, C2 -1 and C3 is 2. Okay, so therefore vector coordinate vector with respect to basis S is given by 1, -1 and 2. The solution of C1, C2 and C3. Okay, for answer B, so answer B, find the vector V in R3 whose coordinate vector with respect to the basis S is given by this. So this is opposite to this one. So these two have the opposite solution. Okay, the approach to the solution. Okay, now in B, so V is a linear combination of V1, V2, V3. So we put back C1, V1 plus C2, V2 plus C3, V3. So solve this. And finally, we get the coordinate of vector V with respect to basis S as this one. Okay, now dimensions. Dimensions of vector space V given by norm DIM. V is the number of vectors in a basis for V. Example, now determine a basis for and the dimension of the solution space of the homogeneous system given by this system of linear equation. Okay. Okay, now to solve that, using Gauss elimination method, we have got the general solution of this one. Okay, we have got the general solution of this by using Gauss elimination method. Okay, now the solution vectors can be written as, so put back this x1, x2, x3, x4 and x5 here in this form. Then we split. Okay, we split into addition of vectors. Put the first vector as variable s, second vector as variable t. Split this one into an addition of two vectors, and we simplify, taking out variable s out and t out, and only values inside. So we have s plus times this vector plus t times this vector. Okay, and these two vectors become v1 and v2. So shows that the vector v1 and v2. Okay, so this is the basis that span the solution space. So since they are also linearly independent, we need to show that the at least linear combination C1, C2, C3 is not 0. So therefore V1 and V2 make a basis, and also the solution space is two-dimensional. So dimension refer to how many bases are there. So since we have two vectors, We have two vectors formed as a basis, so therefore the dimension of the solution is 2. Okay, next is row, column and null space. Okay, let A be matrix M times n. Then subspace of Rn spanned by row vectors in A is called the row space of A. Subspace of Rm spanned by column vector in A is called the column space of A. And subspace of Rn spanned by the solution vector in homogeneous system Ax equal to 0 is called the null space of A. Example, for M times n matrix given by this, the vector, mean that first row, second row and the last row in Rn from the rows of A are called the row vector of A, and the vector in the row form are called the column vectors of A. Okay, example, base for row and column space of R of this one is in the row echelon form, and this is a row echelon form, and the vector row 1, row 2, row 3 form the basis for row space of R. Right? And the vector C1, C2, C4, which is a matrix A in the row echelon form a basis for the column space of R. Okay, example, find base for the row and column space of A. This one. Okay, now this matrix using ERO transform into row echelon form. So finally you will get this one in a row echelon form using ERO. So basis vector are row 1, which is non-zero. Non-zero vector row mean vector row 1, row 2 and row 3. Row 1, row 2, row 3, which is non-zero row are the basis vectors. Are the basis vectors for matrix A. Okay, for matrix A. The first, third and fifth column, the first, third and fifth column, 1 here, and then one leading one here, and another one here. Okay, so this is column 1, column 3 and column 5. Okay, so we have column 1, column 3 and column 5 form a basis for column space of R. Thus, the corresponding column vector of A. So we refer back to the column here. We refer back to column 1, column 3 and column 5. Okay, column 1, column 3 and column 5. We refer back to the original matrix. So it becomes C1, C3, C3 and C5 form a basis for column space of A. Okay, so we need to do the ERO in order to find basis for row. For basis for row space, we take the non-zero row, the non of the ERO form. Okay, the ERO form. We take the non-zero row as basis for row vector, which is R1, R2 and R3. But for but for basis for column space, we take the corresponding column. We take the column which has a corresponding 1, okay, and refer back to its original column in the first matrix A. That will be a basis for column space of A. Okay, last one in chapter 5 is rank and nullity. Okay, nullity of a matrix is the dimension of its null space and denoted by nullity A. Okay, alternative definition of rank. Rank of matrix A is the dimension of its row and column space and denoted by rank A. If A is an m times n matrix, then rank A plus nullity A makes n. Example, find the rank and nullity of this matrix. Okay, solution. Okay, now use ERO, get the RRE form of matrix A. So finally you will get this using ERO in the RRE form. So the 2 non-zero row is the row space and column space are both 2-dimensional, so rank equal to 2. Okay, so this is the basis for row vector, the first 2 row here. Okay, and the 2 non-zero row, 2 leading one. Okay, leading one here, we have this column and this column. We form a basis for column space. So, to the number of leading 2 make dimension 2. So, the dimension for matrix A are 2. So we have 2-dimensional, and the rank also is 2. Rank, we've got rank from how many non-zero row available. Okay, so rank E or a dimension. Rank also is another way to another name for dimension. Okay, so rank of matrix. Rank normally is applicable to matrix, and dimension is applicable to vectors. Okay, so rank A refer to dimension of vectors. So now rank of matrix A is 2. Now to find the nullity of A, we must find the dimension of the solution space of the linear system AX equals 0, homogeneous system. Okay, now the corresponding system of equation will be, so we write this in the form of system equation. Write this in the form of system equation. So we get this one. Now we get this one. And write x1, x2 in a linear combination of other variable. Okay, so we have this one. Right. And finally, so we have a general solution. Okay, x1 and x2, we already x1 and x2 in this other variable. Okay, so let x3 become R, x4 become S, xs become T, and x6 become U. So we can write x1 and x2 in this combination. Okay, so now put back the solution x1 until x6 in the combination of R, S, T, and U. Okay, so we take out the symbol or letter R, S, T, and U, take it outside, and inside is only component of vectors. So what we got from this is a combination of this. Okay, so if we multiply in R, S, T, and U, we'll be able to get again this equation. So from here, we split into a combination of vectors. So since we have 4 vectors, now it forms a basis for the solution space. So this is the basis for the solution space. Okay, so since we have 4 bases for the solution space, so the nullity of A is 4. So that is how we obtain rank of A and nullity of A.